In this episode, we will talk about AdaptThink. Reasoning models can learn when to think. We're diving into these large reasoning models,
Yeah.
systems that can really problem solve almost like we do.
Yeah, models like OpenAI's O1 or DeepSeek R1, they're showing some pretty amazing abilities on complex stuff.
And a lot of that comes down to how they, well, think, right? They go through these long internal processes.
Exactly. It's like this deep deliberation. They explore different solution paths. They might reflect on intermediate steps, double-check their reasoning, all before giving you an answer.
Okay, but let's talk about the practical side for, say, a software engineer listening. That deep thinking sounds great for accuracy, but what does it mean for performance?
That's the trade-off. It means higher inference overhead, longer processing times, more compute needed for every single query.
Right, increased latency, maybe higher costs. That can really slow things down in, real-world applications where users want fast responses.
Precisely. It can become a real bottleneck.
And here's the interesting part, the inefficiency. These powerful models, they often seem to do this heavy lifting even for simple questions.
Whereas probably overkill. Some research has pointed this out, model sort of overthinking easy queries.
It's like using a massive enterprise system to add two numbers, just not efficient.
So that raises the key question. Can we make them more efficient? Can we optimize this without losing that problem-solving power?
And one idea is this concept called no thinking.
Right. Basically prompting the model to just skip the long thought process and give the solution directly.
How do they actually prompt that?
In this research we're looking at, they kept it simple. They just use an empty thinking segment in the prompt.
Think. Okay, so it's like signaling you could think here, but maybe you don't need to.
Exactly. And what's really interesting from early studies is that for the simpler problems, this no-thinking approach, it can be just as accurate, sometimes even more accurate, than the full thinking mode.
And presumably much faster, fewer tokens generated.
Significantly fewer, yes. Much more efficient.
So this brings us right to the core idea we're exploring today. Can these models actually learn to choose? Can they adaptively switch between thinking and no thinking, depending on how hard the problem looks?
Could they learn to allocate their own sort of cognitive resources more intelligently? That's the goal.
Enter AdaptThink.
AdaptThink, it's a novel reinforcement learning algorithm, RL, designed specifically for this, to train models to figure out when to think deeply and when a direct answer is better.
Potentially giving us efficiency without losing that accuracy.
That's the hope. Big gains in efficiency, maybe even keeping or improving performance.
Okay, let's dig into the motivation. You mentioned no thinking being good for simpler tasks. How did the researchers pin that down?
They did a pilot study using the Math 500 dataset. It's useful because it categorizes math problems into 5 difficulty levels.
Right, from easy to quite hard.
Exactly. They took the DeepSeek R1 Distill Quinn 7B model and had it generate answers for problems across all these levels both ways, standard thinking mode and this not thinking mode.
Did they limit how much it could think?
No, they gave it a pretty generous token budget, 16,000 tokens, so the thinking wasn't cut short artificially.
Okay, and the results. The paper has figure 2 showing this. What did it reveal?
Figure 2 really tells the story. First off, for the easier problems, levels 1 to 3, not thinking, accuracy was right there with thinking, sometimes even better.
Better, even without the detailed thought.
Yep, especially on level 1, the easiest ones, not thinking, actually outperformed thinking. It suggests that for really simple stuff, the long thought process might just be noise, or even counterproductive.
That is surprising. You'd intuitively think more processing equals better answers.
Not always, it seems. And figure 2 also showed, as you'd expect, that the average response length in not thinking mode was way shorter for these easier levels.
Makes sense. No chain of thought text being generated.
Right. And shorter responses mean lower inference costs. Direct win for efficiency.
So less processing, shorter output, same or better accuracy on simple things. What about the harder problems?
As you'd guess, for the really tough problems, thinking generally gave a better shot at the right answer. But they also looked at something called the instance-level pass rate.
Which means?
Basically, did the model get the right answer at least once if it tried multiple times? Their analysis found that the thinking process only significantly boosted this pass rate for less than half the problems in levels 1 through 4.
So even for moderately hard problems, the heavy thinking wasn't always the key difference maker.
It seems not consistently, no. The no-thinking approach could often get there, too.
Okay, so the big takeaway seems to be deep thinking really pays off for the most complex challenges. But for a lot of problems, maybe even up to moderate difficulty, no thinking is just as good, maybe better, and definitely more efficient.
Exactly. That observation that the need for deep thought depends on the problem's difficulty. That's the core motivation behind adapting.
All right, let's get into the AdaptThink algorithm itself then. How does it actually teach a model to make this choice?
It's built around two main ideas. First, a specific kind of optimization objective one with constraints. Second, a clever training strategy using important sampling.
Okay, let's take the first one. The constrained optimization objective. What's the goal there?
The main goal is to push the model to use no thinking more often, and this is crucial without letting its overall accuracy drop compared to how it performed initially.
So maximize Another King usage, but keep performance level.
Precisely. Maximize the probability of choosing no thinking under the constraint that the accuracy stays at least as good as the starting point, the reference model.
How did that look mathematically? Equation 2 in the paper.
Yeah, equation 2 lays out that initial problem. Maximize the expected chance of picking the no thinking action, subject to the expected reward think accuracy of the trained model being greater than or equal to the expected reward of the original reference model.
Optimization with constraints can get tricky. How do they simplify that?
They convert it into an unconstrained problem by adding a penalty term. That's equation 3. If the model's accuracy dips below the reference level, it gets penalized.
And there's a weight for that penalty, lambda.
Right. Lambda controls how strictly that accuracy constraint is enforced. It's like a knob you can tune.
Balancing efficiency preference versus accuracy maintenance.
Exactly. Then they do a bit of algebraic rearrangement, introduce as 1 over a, that's equation 4, and arrive at a form that's easier to work with. It focuses on maximizing a combination of an indicator for choosing not thinking and the reward difference compared to the reference model.
Okay, but how do they get that reference model's expected reward? You can't test it on everything. Equation 5 mentions pre-sampling.
Right, it's an approximation.
Yeah.
Before AdaptThink training starts, they take each problem in the training set and have the original model generate, say, k different responses.
Okay.
They calculate the average accuracy across those k responses for that specific problem. That average, r bar ref of x, becomes their practical estimate of how well the reference model does on that problem.
So they establish a baseline for each training example. How does this feed into the final objective, equation 6?
Equation 6 is the simplified objective they actually maximize during training. It's the expected value of this combined signal, times 1 if it chose no thinking, 0 otherwise, plus the actual reward it got minus that pre-calculated reference reward r bar ref.
Got it. Now, choosing no thinking or getting an answer right wrong, those aren't smooth, differentiable things. How do they optimize this with gradients? They mention policy gradient and PPO in equation 7.
Correct. They need reinforcement learning here. They use the policy gradient method. And for stability, they use a loss function structure similar to proximal policy optimization, PPO, but without the usual KL divergence term.
Okay.
The key piece is the advantage function, AXY. They define it as that no thinking indicator times bad plus the actual reward minus the reference reward. This advantage tells the model whether choosing thinking or no thinking for a given problem led to a better than expected outcome.
That makes sense. So that covers the optimization objective. What about the second component, the important sampling strategy? Why is that needed?
It solves what they call the cold start problem. An off-the-shelf model usually defaults to thinking. So if you just start training AdaptThink naively, you might hardly ever see the model try no thinking.
So it wouldn't get any data to learn when no thinking might be good.
Exactly. It's hard to learn the value of something you never experience.
So how does important sampling help bootstrap this?
Important sampling lets you learn about one distribution using samples from another. Here, they design a special sampling distribution, IS in equation 8, specifically to generate a good mix of thinking and no thinking examples for training.
What does this special distribution do?
The clever part is how it handles the very first token the model generates. For any given problem, there's a 50% chance it forces the first token to be think.
Which forces the model into not thinking mode right away.
Right. And the other 50% of the time, it forces the model to start with a token that usually begins a thought process like, all right, was their example. After that first forced token, it just follows the model's current policy.
So, by controlling that very first step, they guarantee that every training batch has roughly half thinking examples and half no thinking examples, no matter what the model currently prefers.
Precisely. It ensures the model gets exposed to both strategies right from the start and throughout training. It prevents it getting stuck in just thinking mode early on.
And this leads to the final AdaptThink loss function, LAT, in equation 9.
Yes. The structure is like the PPO loss, but the crucial difference is that the training samples are drawn from this important sampling distribution, ISER, not just the model's current policy. This makes sure both kinds of trajectories inform the updates.
And algorithm 1 basically outlines this whole process. Pre-sample for the reference reward, then iteratively sampled using importance sampling, calculate advantages, and update the policy using the LAT loss.
That's the procedure. And the importance sampling keeps helping throughout, letting the model continue to explore both options.
Okay, that loss function, LAT, still seems a bit complex conceptually. Can we get a simpler intuition? Equations 10 and 11 try to clarify when it favors no thinking.
Yeah, let's break it down. Equation 10 looks at the average advantage for each mode. For thinking, the average advantage is just its average accuracy minus the reference accuracy.
Okay.
For no thinking, the average advantage is its average accuracy plus that emic incentive minus the reference accuracy.
And equation 11 says no thinking gets favored if its advantage, including Goto, is higher than both the reference and the thinking advantage.
Essentially, yes. No thinking is preferred if its accuracy, potentially boosted by that value, is competitive with or better than both the baseline and what thinking achieves.
So Malacca acts like a threshold. If the accuracy gap between the modes is smaller than law, the algorithm says, go for efficiency, choose no thinking.
Exactly. But if no thinking causes a big accuracy drop, much larger than model, the loss function will push the model back towards thinking to protect performance. It neatly encourages not thinking for easy stuff and thinking for hard stuff, just like the motivation suggested.
Okay, the theory sounds solid. Let's talk results.
Ah.
How did AdaptThink actually perform in their experiments?
They ran quite a few tests. They started with 2 versions of the DeepSeek R1 distill-Q model, a 1.5 billion parameter one and a 7 billion one.
And trained them on.
A dataset called DeepScaler, about 40,000 math problems from various sources.
And they evaluated on math problems too.
Yes, 3 datasets with increasing difficulty, GSM-8K for grade school math, Math 500 for high school competition math, and then the really challenging AME 2024 for Olympiad-level problems.
Measuring accuracy and response length.
Those were the main metrics, yes. Accuracy and how long the generated response was.
Table 1 has the main results. What jumps out?
The efficiency gains, really significant reductions in average response length compared to the original models. We're talking 53% reduction for the 1.5B model and over 40% for the 7B model, averaged across the test sets.
Wow, that's cutting the output length almost in half in one case. But did accuracy suffer? That's the crucial trade-off.
That's the surprising part. No, accuracy actually went up slightly on average, about 2.4% increase for the 1.5B model, 2.3% for the 7B.
So it's more efficient and slightly more accurate. That's genuinely impressive. A real win-win.
It really is, and it outperformed most of the baseline methods they compared against, especially those that only try to optimize within the thinking mode. AdaptThink's adaptive switching seems key.
Table 1 also has that ration T column. What's that showing?
That's the percentage of times the model chose no thinking, and you see a clear pattern. AdaptThink uses no thinking much more on the easier datasets, GSM-8K and Math 500. But for the super hard AIM problems, it switches heavily towards thinking.
So it really is adapting based on difficulty. That's exactly what it was designed to do.
Precisely. It learned the strategy.
And figures 3 and 5, looking at the Math 500 difficulty levels, confirm this visually.
Yes, those charts clearly show the trend. Lots of no thinking for level 1, then progressively more thinking as you go up the levels. And importantly, AdaptThink's accuracy was generally higher than using only thinking or only no thinking across most levels.
So the adaptation itself provides a performance benefit beyond just picking the better of the 2 original modes.
It seems so. The RL training fine-tunes the model overall.
Yeah, the paper digs deeper too. They looked at the effect of that pay parameter in Table 2. What did varying node do?
Just as expected, wire controls that efficiency-accuracy trade-off. Increase may, and you tell the model to prioritize efficiency more strongly.
So more no-thinking responses.
Yes, a higher ration T and shorter average lengths, but the accuracy gains start to diminish slightly with very high ORCA values.
Makes sense. You push too hard for efficiency, you might start hurting performance a bit.
Right, but what's interesting is that even with all set to 0, so no explicit reward bonus for no thinking, the model still chose it over 50% of the time on the easier datasets.
Meaning no thinking is just inherently better for some simple problems, even without being nudged.
It looks that way. The analysis showed AdaptThink is pretty robust, though. It reduced length and improved accuracy across most of the values they tested.
And what about the important sampling? Figure 4 compares AdaptThink to a version without it, called GRPO.
GRPO stands for Gradient Ratio Policy Optimization. It's a more naive RL approach that doesn't use that special sampling strategy.
And how did it do?
It struggled. Because the initial model prefers thinking, GRPO didn't get enough no-thinking examples early on. Figure 4 shows it mainly improved accuracy within the thinking mode, but barely reduced the response length at all.
So it couldn't learn the efficiency trick.
Exactly. AdaptThink, with important sampling, got that balanced diet of both modes from the start, allowing it to learn when no thinking was beneficial and dramatically cut down the response length. It highlights how crucial that sampling strategy is.
Okay, another interesting point was implicit thinking. Could the model be sort of thinking under the hood even in no thinking mode? Table 3 looked at this.
Yeah, the concern was whether the RL training might have just pushed some reasoning steps inside the final answer generation, even when it outputted the think tags.
How do they check that?
They analyzed the text of the no-thinking responses from AdaptThink, comparing them to original no-thinking responses and the final answers from original thinking responses. They looked for keywords like, wait, let's see, hold on, things that suggest reflection.
Did they find much of that creeping in?
Table 3 shows only a slight increase in those kinds of keywords and a small increase in the length of no-thinking responses, mostly for the larger 7B model. It wasn't a huge effect.
And they suggested a fix.
Yeah, they proposed potentially giving 0 reward during RL training if a no-thinking sample contains those implicit thinking keywords, which could discourage it further.
Finally, how well does this generalize? They tested it on MMLU, which is way outside the math training data. Table 4 and Figure 8.
Right. MMLU, Massive Multitask Language Understanding, has questions on history, science, law, all sorts of things. Very different formats, too. It's a tough out-of-distribution test.
And AdaptThink.
It still worked surprisingly well. Table 4 shows it cut the average response length on MMLU by over 30%.
Wow. How often did it use no thinking there?
About 16% of the time. And importantly, it still achieved higher accuracy than the original models, even on this completely different data set it wasn't trained on.
That's strong evidence for generalization. Figure 8 had an example.
Yes, a top 3 question from MLU. AdaptThink correctly identified it as relatively simple and used no thinking, getting it right efficiently despite the domain shift.
And the other case studies in Figures 6, 7, and 9 just drive the point home, right? Showing the contrast between verbose original models and concise AdaptThink on easy problems.
Exactly. GSM-8K, Math 500 examples showing that clear difference.
And then Figure 9 showing AdaptThink correctly, choosing thinking for a really hard AIM problem.
Right. It demonstrates the adaptive behavior across the spectrum. Simple problem, go direct. Hard problem, engage the reasoning.
Okay, so let's try to wrap up this deep dive. AdaptThink looks like a really effective technique.
It does seem very promising. The core finding is that it successfully teaches these models to switch between thinking and not thinking based on how hard the problem seems.
And the benefits are clear. Big cuts in inference cost that response length reduction.
Yeah.
But also somehow managing to improve accuracy too.
Yeah, that combination is powerful. It offers a way to manage that trade-off between reasoning quality and efficiency, which is becoming more and more critical as these models get bigger and are used more widely.
Now, the researchers did mention some limitations.
They did. The experiments were mainly on 1.5B and 7B models, so scaling to truly massive models is a next step. And the training was heavily math-focused.
Although the MMLU results suggest it can generalize.
Definitely promising, but more testing on diverse data sets, maybe with verifiable rewards for non-math tasks, would be good future work.
Absolutely. So as we finish up, here's something for you, the software engineer listening, to think about. As AI like this gets integrated more deeply into software, how might these adaptive reasoning strategies change things?
Could we see systems that dynamically adjust their effort based on the task? Maybe less processing for routine things, more for critical decisions.
Leading to more efficient, maybe more responsive AI interactions within applications. It feels like a really interesting direction for making AI more practical and maybe more human-like in its resourcefulness. Definitely something to watch.